Welcome back. So, this is the last segment of this course, and what I am going to look at in this case is stress strain properties in different planes. So, we start with that as we looked at for the Lennard-Jones system. It was a very simple system. So, what I will do in this segment is show you a few applications, so that you understand how molecular dynamics is applied, and we will also look at a VMDL. And then I will conclude this segment in terms of how we use the entire models in order to calculate some of the deformation of the material. And there are lots of papers available now, and I will have a list of references for you in your website, where you will look at all these kinds of deformation properties, which where you look at the crack tip propagation, the fracture mechanics, and the ductile to brittle transition. They are looking at the dislocation movement in the semiconductor. So, you can calculate the electronic properties, etc. So, there is a lot of research going on. It is a very hot field. So, if you look at here, we start with the stress strain. So, looking at our elastic constant from Cauchy-Born rules as we described, we can calculate the stiffness matrix Sij and also the compliance matrix Ijkl with using all these different terms that we calculated from Helmholtz free energy. And so, small deformation first order elastic terms, we can again look at summation of all these strain terms and then calculate the overall energy of the system. And so, this expression is obtained by expanding the potential energy up to the second order term. So, you can then use second order terms in order to calculate all these stress and strain, which we will look at. So, if you look at a triangular lattice with Lennard-Jones potential, then if you look at, again, this is a very simple Lennard-Jones potential that we will also use in VMDL. Then you can see how the elastic limit, where there is elastic stress strain, and then you are looking at the strain in 1 0 0 direction. So, this is how you are able to calculate in a triangular lattice. So, now let us look at a particular case that I did with EAM copper with 500 copper particles. We used the EM potential by Foils and Baskis, and we looked at the FCC structure. So, we looked at the 500 copper particles put in FCC structure, runs were made over 20,000 time steps, and then we changed the strain from 1% to 10%, and then I calculated stress strain curve of the copper, and based on that we came up with the elastic constants. And as you know, this is FCC cubic. So, you have only 3 elastic constants, C11, C12 and C44. So, now if you look at this, this is a simple calculation between stress and strain by increasing the volume of the cell and then calculating the stress, which is calculated in terms of the virial pressure, and this is the within elastic limit. So, the slope of this is giving me the elastic constant. So, for a cubic crystal, obviously I have to calculate sigma 11, sigma 12, sigma 33. So, the way they are calculated is multiplying elastic constant by the strain. So, the strains are happening in principal direction and then the 2 cross directions as well. So, this is where we are using eta 11, eta 22, eta 33, and then we are looking at the shear modulus as well, and what is the strain in the shear directions, which is gamma 12, gamma 13, gamma 33. For a system with cubic symmetry, we know that we only have C11, C12, C44. Using these 3 stiffness constant, the stress sigma and strain eta can be related by the following equations. So, this is how we are calculating it, and you saw the calculations. Now, here are the comparisons of based on the 20,000 time step that I did in all different directions, C11, C12 and C44. So, now you can compare the data. So, this is by EM potential people, Foils, and this is the 1986 paper, where and another one is Simmons and Wong, which was done without EAM, and what present work is the work that I did. So, if you look at C11 1.67 and my calculation shows 1.6716, which is very good match here, and experiments gave 1.70. So, this is what we call is the amazing part of molecular dynamics, because with 500 particles I could calculate C11, which is very close, even 1 or 2% with the accuracy of the experimental data. And so, now you look at C12, which is the cross directions here. So, see 1.24, and obviously I have very good match with the foils because I am using their potential function, say 1.241, and if you look at the experimental is also very good, 1.225. Now, C44 we are looking at 0.767, very good match. Now, if you look at the E energy in terms of arc per centimeter cube, we are also looking at energy very nicely. We are looking at the other parameter which have very close match, and this is where we conclude that molecular dynamics, especially with EAM potential for the metals, works very well. And also you saw that C12 is not equal to C44, and that is what Lennard-Jones potential could not do. So, with the many body potential EAM, embedded atom method potential, you are getting accurate numbers with 500 particles. So, that is the power of molecular dynamics. So, now using the same thing, we can also look at the brittle to ductile transition and a whole bunch of other things that I discussed earlier. So, now let me do a VMDL that we have done earlier, but now you understand it much better. So, I am going to do it very quickly, explain to you. So, let us make that as big. So, we have available that, and I am going to expand that, magnify that. So, you have that. Okay. So, let us do, and again this is we have obviously a piston which is important here, and let us show the averages. These are 0 0 at the beginning. Let me make magnification slightly lower. Okay, that should be good. Now let's make it big. So, now in this case you are looking at the simple calculation, and this is with the piston. So, we are looking at the piston, and because we are doing stress strain curve, we want to start with the pressure, in this case 1.0, and piston mass is 1.0. So, now we define the stress strain curve very well. We also know the length here based on the volume. So, I am going to start this. So, now you can see that this system is at TPN pressure and temperature. So, let us look at the volume is changing, but is sinusoidal. This is another sinusoidal curve, and this is TPN, and we are looking, let us say, show the real units. Let us also put these real units. So, now we are looking at the system getting to equilibrium, and this essentially sinusoidal curve will damp to almost close to a straight line, which is what is happening now. And pressure is important because we are doing stress strain. So, here you have two parameters available. Pause it here. You are looking at volume in meter cube, and you are looking at pressure. So, because you know the length of this particular structure which we have put in FCC, for example, we can now calculate the changes in the directions of the stress, and if because it is anisotropic, we only have to calculate sigma 11, sigma 12, and sigma 44. So, now if I have to ask you to do this calculation, you are going to start that, and we already did equilibrium now. So, I am going to increase the pressure and keep the piston volume same. So, we go forward. Now, you can see that it is moving down, and the strains are available all over the place, and this has no walls. So, this is a periodic boundary conditions, which is good. We want to look at the bulk elastic constants. Now, let me stop it, pause it here, and then increase the pressure again and move that. So, stress strain curve is being generated as we speak, because I am understanding what is the pressure at this particular and what is the volume. So, I have stress and I have the strain, the change in volume. So, I stop it here again. I take another value. As I said, I took 10 values from 1% strain to 10% strain, or in this case stress increasing into 10 parts. So, let us go forward. Now, you are also again seeing the change in the volume and the pressure. So, now let us take some extreme pressures, and then let us see what happens to the system. Now, you can see it is pushed down quite a bit. So, now you have stress strain curve which is in the elastic limit, because things are not broken up. If we want to break them up, then obviously you increase the temperature, and then all the elastic constant becomes soft, and then they break down. So, this is where by doing different kinds of pressure we can go to the strain, and that is where we can do all kinds of elastic experiment. Deformation is very important factor. So, just to summarize, we start with thermodynamics, we start with statistical mechanics, we understand how we formulate different kind of systems, we understand now how to calculate properties which are the thermodynamic properties. Then we talk about the properties like mean square displacement, radial distribution function. Then we connect them with our Green-Kubo formulation with linear response theory. So, that now we can find thermal conductivity, viscosity, etc., the transport coefficient, and then we can also do using Parnello-Rahman conditions as well as using Carr-Parnello method with what I would say electronic structure potential function, very accurate. We can understand the atomic stress and then understand how different systems would fail with different kinds of crystal structure. So, now this gives you entire set of tools and the methodology, both Monte Carlo and molecular dynamics, which allows you to now be a very good molecular dynamist and look at all different kinds of complex situations which are thrown at you, both in the biology, chemistry, electrical engineering, mechanical engineering, mechanics, and you can solve amazing amount of problems, and that makes you highly employable now. Thank you very much.